Hello, good day. So today I will be discussing um, AVL or Athena Lattice Vortex by Mark Drela and what you can actually do with this software and how to use it a little bit. Because I think I looked for some videos and I didn't really see anything about how to use it, and some students have been asking me, hey, how do you use this software? Is there any, how can you teach me how to use it? And so I think it's quite straightforward, but I think that there's a bit of a steep learning curve. So this video hopefully will introduce you a little bit into how to define the geometry in particular, which I think a lot of people have problems with. And then also show you exactly what you can do with it, because I think it's a very powerful tool. I think there's a lot of other things, a lot of tools out there like .com and OpenVSP, but I particularly like this software. It gives you a lot of aerodynamic derivative data, and you don't have to worry about whether or not you can model it rudder like you have to do with .com and these kinds of things. So I think it's pretty useful. So let's have a start. So I will first show you So I'll first show you the software, like what happens when you go down on the website and you just download this, and it's just a single executable file. There's also some documentation, which I think is a bit intimidating to read, which is why I think that a lot of people don't use it. And then there's also some sample input files which you can use as a template for your aircraft. This AVL is for fixed wing aircraft. It's not. I don't think you can do it for. Don't think it's very useful for helicopters and rotorcraft. Probably another reason why people don't use it. Anyway, so so let's have a look at what you get and what you need, basically the files. So you get the avl.exe file. Next thing that you need is a geometry definition file, which usually has a .avl extension. You need a mass file for reasonable aerodynamic analysis and calculations, and you need a trim or a case file. The case file defines the flight condition that you will be operating in. So it defines things such as let's have a look at it. It defines things such as the velocity, the alpha, if you want to set an alpha constraint, a parasitic drag, air density, which will then represent the altitude that you're at, and these sort of things, right? So I'll show you how to use these things as you go along. So I'll show you so I have an aircraft here, and I'll show you what the geometry looks like. So when you open AVL, the first thing you do is you need to load a geometry file. You need to load that geometry file, and I'll show you what it looks like in a bit. But I just want to show you what my geometry looks like, so you get a better idea when we actually do go into the geometry definition a little bit. So let's load it, and if everything works okay, then you get this sort of then it doesn't crash, basically. So once you do that, you go into the upper menu, and then you type G, and you can basically see the geometry a little bit. So this is my geometry. I have a very high aspect ratio. I just modeled the main wings, the vertical fin, and the horizontal tailplane. I left out the fuselage, because the fuselage, if you want, you can define a body. A body looks like this, but sometimes you get some better results without it. You have to decide for yourself and do some kind of validation, which I'll show you basically how to do in a little bit. So how I get this geometry is from my geometry definition file, which is this. So this is what the geometry file looks like. The first thing that you need to do is you define your reference lengths, which is typical. I mean, if you do any aerodynamic analysis, you usually have to define the span, the chord reference, and the surface area, the chord reference, and the span. You need to define a CG. So this data you initially need. You need some estimate of this data. The second thing, so then once you have that, your surface, AVL works with surfaces and sections basically. You define a surface first, so my surface in this case would be my main wings. This is the first surface I've defined, and then my surface, my main wing, is divided into sections. The N chord, C space, N span, and S space stands for the number on the chord. I think this is span-wise. This is span-wise, chord-wise spacing. The number of divisions on the span, and then the span-wise spacing, which corresponds to these pink lines and these white lines that you see going across here. No, I'm no aerodynamicist or expert in any way. So you can kind of, I think there's some guidelines on in the documentation document if you want to really fine-tune this and get really know how to really go about doing this as optimally as you can. You can define a twist angle. You won't actually see it on the geometry, but it will be there in the loading distribution and lift distribution calculations, which I'll demonstrate shortly. So let's start a section. So a section is defined by an X, Y, and Z point, and then a reference length. So I'll show you how this works. So I have a little drawing here. Basically, let's close this for now. So I have a little drawing here, and from this you can see that the X position I've defined here is 14.8 meters, which means that I have started the main wings at 14.8 meters behind the nose of the fuselage, right, which corresponds with like around here. And then so my Y position is 0, which means it's at the center line of the fuselage, and then I've defined it at a particular height. And then what happens is this chord length corresponds to so it basically draws a line starting from this X, Y, and Z position point, and it draws it as long as the chord length that you have defined, which is 4.461, as I have defined. So then what you do is you then define another section at a Y position further away from the center line, which I have defined here as 0.95, which corresponds to this line here labeled 1. And what it will do, so once I do that and I've defined it as the same length, so basically what it will do is it will just define like a square sort of panel. As you can see here, I've also defined it in the same X position. So it starts at this point here, and it will draw another line here equal to the same chord length as the previous section, and it will create like a little rectangle. And then what will happen is, and then the next section, well, let's skip this section and then go on to this next one at 2.022, 2020, right. So this will be at this dashed line here. I've created that next section, which has an X position a little bit further back because this wing does have some sweep angle of 20 degrees, and then at a further Y position away, and then my chord length, because this also has some taper, the chord length does decrease a little bit. You can get this data basically from a CATIA model is the best thing, I think, but you can also work with a simple sketch like this, and I did this in Visio, so you can actually use this and get a rough idea as to what for the geometry to put into AVL. And then so once you define like a number of sections, AVL will simply just join all of these. It will just create a panel or section. It will just complete that section for you and kind of linearly interpolate along the between the sections to create that surface. This Y duplicate, you only need to do it once, because once you put this Y duplicate, it will just create the one on the other side for you by duplicating this one. One thing to note is that you do need to create your sections at the points where you have control surfaces. So for example, I have a flap which starts at 2.022, which is why I created this section here. So my inboard flap starts here, and then it continues. So you have this flap, that starts here at this section, you have to define control surfaces at section points. You can't just define them arbitrarily. So, and then I have it continues on through section 3, and then it ends, I think, somewhere at some later section. But that's how this thing works. So if you have a control surface that spans from section 2 to section 4, you have to include that flap, or that control surface. You have to include this control keyword as well as the control name, the same control surface name at each section until it ends. So as you, let's see, it ends somewhere along section 18.752. so mine ends at 4, which is right here, right? And as you can see here, the flap no longer exists. So it just means that you define it at the start and the end section, as well as each section in between. So that is enough of the geometry. I think you define another surface for the horizontal tail plane, and then you define another one for the vertical tail plane, and you basically do the same thing. You can also define custom airfoils using this AVL command, but you have to make sure that the file is actually inside inside the same folder. Or you can use like a NACA airfoil, standard NACA airfoil, and it will bring in the same geometry. It will bring in that airfoil and use that for the calculations. So that's it for the geometry. So let's go back into AVL. I don't know what's going on. I don't know what that is. Right, so let's go back into AVL. So we have the geometry defined. The next stage of what goes on here is that you need to, when you do your aerodynamic analysis, is you need to now put in your mass file. That's the next stage. The mass file, so at the main menu just type in mass, and just the name of your mass file, right? And you will see here that it brings in all the inertias, and it brings in the mass data and the CG again, and then you just type in mset to make sure it applies to all the run cases that you will then input, which I will show you now. So for the cruise case, which you saw before, you go into the upper menu, you type F, and then you type in the name of the file, cruise case.run, and then you can see what it has done. It has started to put some constraints. So I wanted to trim the aircraft, so I said AVL doesn't know anything about your control surfaces or what they're used for specifically. It doesn't know what an aileron is. So you have to tell it that the aileron, I want to use the aileron to provide 0 rolling moment, and then I want to use the elevator to provide 0 pitching moment, and I want to use the rudder to provide 0 yawing moment, and that will trim the aircraft. Now you also need to trim for a particular flight condition. So we had actually put in that, and you can check it using M. And then just have a look at it, make sure it looks okay. And to trim the aircraft, you need to use the C1 menu. So C1, set level or banked, so you can actually bank it and still set a rolling moment of 0. It'll just stay with a constant bank angle. So when you use the C1 menu, you'll have a CL. It will compute a CL to trim at a particular velocity. So if you change this velocity, obviously CL will change. And then you can just check these parameters and make sure they're correct, and that you want to trim it at that angle. You want to trim it at this CL and these sort of flight conditions, and then you just type in X to execute the flow calculation. And once it converges, you will have you can see here that it has provided for that CL you need a alpha or angle of attack of 2.89. It will give you the coefficients, CL total and CD total, and it will give you also the elevator deflection required to give you that particular angle of attack. Now this I think is particularly useful because instead of doing like manual trim calculations by hand or by MATLAB or whatever, I think this is quite convenient, and all you need to do is just type X and just change the flight conditions. It's quite useful little little piece of software. So once you do that, you can, which is really the real beautiful thing too, is you can now get your entire stability derivatives. Let me output this to a file so you can see it better. So AVL gives you a lot of it gives you a lot of, these are all first derivatives, unfortunately. It does still give you quite, for subsonic, you know, it is aircraft, it is quite useful. So it gives you a CL. One thing to note, which is very strange, this is in radians, but these control surface deflections are actually in degrees. It's per degree, not per radian. But anyway, you can get alpha, you can get you know, all the stability derivatives as well as all the control surface derivatives. It also tells you whether the aircraft is spirally stable and computes the neutral point and these sort of things. You can generate this in the body axis, or you can generate this as the stability axis derivatives, whichever one you would like. And there is also longitudinal and lateral coupling derivatives as well, so you can get CL due to yawing moment if you so wish, which is probably usually quite negligible, but you can still get it. That's quite useful. So I think so further on you can actually do you can see the loading distributions on the wing using the LO in the geometry command. You can get, so, and then if you press K, you can use L and R to basically move around the geometry, and you can see the span-wise loading distribution either through this method, or you can actually use go back to the upper menu and type T, and you can see the loading distribution, the load distribution and the lift distribution curves, and this is useful to check and validate your model a little bit. So if you notice here that my aircraft is typically high aspect ratio, so it's not going to have a very elliptical sort of lift distribution. The CL is what I look at typically, and then you can look at the load distribution, which they have normalized by CRF for some strange reason, and then there's the alpha curves here as well. And yeah, once you see this kind of bending moment, this sort of bend in the lift distribution, you know it's giving you a reasonably good approximation of what it should be, but you have to do some sort of validation on it. So the final thing that I would like to show you is the eigenmode analysis. So you just type in mode at the main menu. It will, if you type in N to use the new eigenmode calculation, it will use the flight condition, the cruise case or whatever case file that you've loaded, and it then shows you this nice pole zero map, which is useful for control surface design, for control system design. So as you can see here, it gives you both the lateral and longitudinal modes. Here you have, like, this is probably a spiral mode. This is your short period pitch, probably Dutch roll, phugoid, and this definitely is your roll mode. And then you can actually go and click one of these and actually examine the mode, and it will bring up. So here, let's see what this is. I'm not sure what this is. All right, so this looks like something like maybe phugoid or something like that. And you can actually investigate this mode a little bit further, and it will give you the damping ratio and the natural frequency of the mode It's very useful for control system design. So let me just investigate another mode and just have a look. X. So let's look at, I don't know, which one would we, so let's look at this one. So this is definitely Dutch roll. You can see it kind of rolling about, doing a little sort of Dutch roll kind of mode. Yeah. So as I said, you can get your damping ratio and natural frequency from this. So lastly, you can also generate your system matrix, which is the linearized system matrix output, from after you have done your eigenmode calculations. I'll show you what this looks like. So yeah, so let's output it. I think you may have seen a flash of it before. Right, so here we have it, and you have the full system matrix output. So this will be correspond, like this will be u dot w dot q dot theta dot v dot, and this will be, and these correspond to your different state variables. And then you also have your B matrix. Basically, this is actually your A matrix here, and this is your B matrix here. You can take this as is and just put it in the MATLAB and just start to do your linear analysis. I mean, if you want to separate it into a lateral and longitudinal, that's up to you, anything like that. So it is generally, it's a very useful piece of software. So I hope this was quite helpful to you, and thanks for watching.